Hi all, I welcome you to this data science tutorial session. Today we are going to be predicting the final placement of a list of PUBG players based on their previous game statistics. I hope all of you here are big fans of the game or data science or both. So without much ado, let's go straight into the agenda. So we're going to start out today by discussing a little bit about the game, introducing all of you to the game and talking a little bit about the problem statement. Then our model is going to begin by some exploratory data analysis on our PUBG data. We're also going to be doing some feature engineering to get new attributes from our data and see how they contribute to the final placement of a PUBG player. And finally, we are going to build a prediction model based on random forests to understand how different attributes in our PUBG data affect the performance of different PUBG players. And our objective variable here is to find out the winning percentile of all the players we have on our list. With that, I come to the end of agenda. Don't forget to hit the subscribe button along with the bell icon to never miss an update from the Edureka YouTube channel. Also, if you want to learn about data science, machine learning, or any other related discipline, don't forget to check out our certification training, the link to which I'll leave in the description box below. So without much ado, let's go straight into the session. So let's move on straight to the demo. The objective of this demo is basically to perform exploratory data analysis on your PUBG data, analyze how different attributes affect the chances of somebody winning the game. You are also going to learn how to detect anomalies or outliers and bust out imposters in this game. We're then going to apply some feature engineering to generate new attributes and find their correlation with the winning percentage. And finally, we're going to try and predict the winning percentage of a certain player by their player ID using a random forest model. So let's go straight ahead and look at our model. Now, this particular model is written in Python, as you might have already guessed. We are using a notebook called Colab to run this model. Now, a quick few things before we begin. Go ahead to the runtime option, select change runtime type, and make sure your hardware accelerator is set to GPU instead of TPU, which will give you a parallel processor with 25 GB RAM. Once it connects and initializes, I'm going to show you that you can see your RAM is 25.51 GB, which we shall be needing throughout this model so as to prevent our model from continuously timing out on us, because this model has some extensive functions. So now the first thing that we're going to do is mount our Google Drive and get our stored data onto this model. So I'm going to run this cell first. And here, as you can see, since we are trying to access a Google Drive, obviously we have to provide some authentication. So click on this URL. It will ask you to sign in. Agree to the conditions by clicking on allow. And you shall be provided with a certain code snippet, which we are going to copy and enter in this field provided for authorization code. And once you're done, you shall see your model output as your code being mounted. So if we try to run this same set of code again, you will see the output given to you is your drive is already mounted. So with that out of the way, let's go ahead and look at our problem statement. Now, for those of you who do not understand the game of PUBG, PUBG or Player Unknown's Battlegrounds is basically an online multiplayer game, which is developed and published by a South Korean video game company called Bluehole. Now, in the game, basically, up to 100 players parachute onto an unknown island and scavenge for weapons and equipments to kill others while avoiding getting killed themselves. Yes. Now, they do have some available safe areas in the game's map, which decreases in size over time as the round proceeds.
This in turn directs the surviving players into tighter areas to force encounters amongst them, and the last player or team that stands wins the round. So this is basically one of those first person shooter type games wherein you can run around, drive vehicles, swim, run, shoot, and kill a bunch of your friends. It's all that clean fun, and experience all the consequences such as a falling too far or running yourself over and eliminating yourselves throughout the course of the game. Now there are multiple different formats of this game. You can play as solo, duo, a squad, or custom, and there is no absolute guarantee of there being 100 players per match, nor at most 4 players per group. Now, each match has its own match ID, players have their own player ID, and if you're on a team, you have a group ID, which will get ranked at the end of each game, depending upon how many teams are still alive when they are being eliminated. Now, the good people at PUBG have made the official game data available for the public to explore and lay analysis on top of outside of the blue circle. All of the data used in this model has been collected from Kaggle, and I shall leave the link for all the data used here along with this model in the description box below. So our main objective here is to explore the data provided to us and layer some analytics on top of it to answer certain questions. First of all, what is the correlation between the number of kills per player and their chance of winning the game, their probability of placing? Our second objective is how do we catch imposters in the game? Here we are going to use different logical conditions based on what we know about the game to determine who is the outlier in the game, or are there multiple outliers in the game. For example, there are players who manage to acquire over 120 weapons throughout the game, which definitely is not possible if you are not using some sort of a cheat. Also, there are people who somehow make 20 kills and all of them are headshots. For that, you would either have to be an extremely skilled player or again, you are a fraudster. And finally, our main goal is to predict how a player places in the game or the probability of a player to win the game. One of the most common methods of doing this is to treat it like a regression problem where we are going to train and test a machine learning model using a regression algorithm. In this case, we are going to be using random forests to predict the final position of a player at the end of the game using their final statistics, which have been given to us by the PUBG team. And we are going to have it from a scale of first place to last place. So let's get straight into it. We're going to start out by importing certain libraries for this project. Let me run this cell real quick while I talk you through it. So we're going to be importing NumPy, which is basically going to assist in applying high-level mathematical functions to arrays. Then we have pandas, which are meant for manipulating tabular data. Then we have a couple of visualization libraries such as matplotlib and the more advanced Seaborn. Then we have iter tools, as well as we have this little thing in the end to ignore warnings. Now that all of these libraries that we need is imported, let's go ahead and load our data. So the first thing we're going to do to load our data is to reduce the size of the PUBG dataset, which is pretty big for a lower or mid-range laptop of common use like the one I or maybe you are using as well. And we have to do all of this without losing any information or with minimal loss of information. So here's what we're going to do. We are going to iterate over each and every column and determine which of them are numeric and can be represented as an integer, followed by finding out the minimum and maximum value. And then we are going to determine and apply the smallest data type that can fit this range of values. Now, what we attempt to do is to reduce the dataset from over 900 MB of data to about 450 MB of data, which is half its size. So at the end of this, what is returned to us is a data frame where all that massive data has been reduced to half its size with minimum loss of information. Next, we are going to load all of those files into the data frame. So here you can see where our training dataset goes and where our testing dataset goes. Each of these are being reduced to an optimum size. And finally, you're going to print the shape of those arrays to determine the dimensions of the tables. So this might take some time. And remember to put in your drive path where you're trying to read your CSV type data from. Very quickly, as you can see, this is the path in which my CSV files are. So if I go to my drive, you can see I have a folder named PUBG data where I have all of these files stored. And here you can see it is the same path to my drive for both my testing and training data. Yes? Now as an output, you can see both of our data frames have been decreased by 65 and 66% respectively. And it has also printed the shape of our data, the dimensions, rows and columns of our data, along with the time execution of this particular statement. Then we're going to go ahead and get the info of the columns in your training data set. So here we have the number of columns. We have 28 columns in total with their data types given on the right. You have objects, you have integers, you have floats, so on and so forth. You've got your group IDs, match IDs, your assists, which is exclusive to all the game formats except solo. Then you have some statistics of kills, kill place, headshot kills, longest kill, and a few distances of ride and swim, along with the number of weapons acquired throughout the game and the placement of a particular player. And here is what your table looks like. Now, train.head is basically going to print the top 5 rows of a particular data set. If it were tail instead of head, it would have printed the bottom 5. So as you can see, you have your IDs, your group IDs, the match IDs, and all the columns, all the 28 columns that we had seen in the cell before. And with that, we are done with our data set. But now that you have your data set, let's understand our data set. Let's get to know our data first before we start working on it. So as I had mentioned before, we're using the data available on Kaggle via the PUBG Developer API. Basically, it comprises of 65,000 games worth of anonymized player data, which have been split into training sets and test sets. Now, for the purposes of this EDA, we are only going to be looking at the training dataset, which comes in the form of a CSV file and contains 4 million rows and 29 columns. Now, aren't you thankful we decided to reduce all that data? So starting out, we have the group ID and match ID. As you guys might have noticed, these are basically meant to identify a group within a match or a match in general. Now, keep in mind that if the same group of, say, 4 players play in different matches, they will be having a separate group ID for each of the match. Now, here we are looking at every individual player's probability of winning. Now, one more important thing, do you think knowing how a player played in one certain match would add any value to our prediction on how the player performed overall? What do you guys think? No, right? Obviously, no. How does it matter if somebody has played, suppose, 100 games? You need to know all the performances to draw out an inference and not a performance specific to a certain match. Suppose I have placed 4th in one game and 6th in another in the same round. How does it matter which exact game have I placed 4th in? I would just take into account that I placed fourth in one game and sixth in another, which is why match ID won't be adding any value to our prediction, due to which in the later cells we are going to disregard it, which you'll have to wait and watch to see how. Then moving on, we have assists and boosts. So your boost can be, as the name suggests, something that can boost a player. For example, an energy drink, painkillers, an adrenaline syringe, so on and so forth. In most of the games that you play, you will have some version of the boost bar available to you where you can see how your digital character's overall health is doing. In this particular game, you will have 4 parts which fill up when a player uses either an energy drink or a painkiller or an adrenaline syringe. And then you have assists. Now, this basically is a feature which is available in every format of the game except for solo, because in a solo game, it's every man for themselves. Why would your opponent try and help you out? True? Then you have the next section, which deals with damage. Now, there are 2 things you need to know. One is damage dealt, which is the total damage your player has dealt with without considering the damage that you've done to yourself, and your DBNO, which means down but not out, which is again a feature specifically not for your solo game. During your duo or squad play, when you lose all your HP, you basically go into this DBNO mode, and in this mode, your duo or squad members can basically come up and heal you, and that is why we basically don't count it as an out. Then you have your headshot kills. As the name suggests, it's the number of enemies you've killed with headshots and the number of healing items used, called heals. Now you can heal basically using 3 items, which are bandages, first aid kits, and med kits. All of these again contribute to your health bar. The next section focuses on kills. You have your kill place, points, kills, kill streaks, and the longest kill. Now, your kill place is basically your position in a match in terms of how many people you've killed. Kill points basically are your external ranking based on the number of relevant kills you've had in your game. Then you have kills, which is the number of players you've killed, followed by kill streak, which is, as the name suggests, it's a streak. It's the maximum number of players that you've killed in a very short amount of time. And then there's the longest kill, which is based upon the distance between you as a player and the player that you have killed at the time of their death. Then you have max place, which is basically the worst placement we have data for in the match. Now, this may or may not match with num groups, which is going to be the next variable I'm going to discuss, as sometimes the data is going to skip over these placements. Then we have number groups, or the number of groups we have data for in this match. Then we have a couple of variables whose names are pretty much self-explanatory. You have revives, which are the number of revives you have done for your teammates, again exclusive to duo, squad, and custom. Then you have ride distance, which is the ride distance, your road kills, number of enemies you've killed while traveling in a vehicle. You have swim distance, which is the same as ride distance, except for it's underwater. Then you have team kills, which, unlike the name sounds, is actually referring to the number of times you have killed your own teammate. Then you have vehicle destroys, or the number of times the vehicle has been destroyed. You have walk distance again, which is distance you've traveled on foot. Number of weapons acquired. We have talked about this variable before. It's the number of weapons you've picked up throughout the course of a game. Then you have win points, which is again the external ranking of a certain player based on the number of wins. This does not happen within a game, but it's a part of our data set, taking into consideration the overall statistics of a player. And finally, we have win place percentile. Now, this is the main variable which we are trying to determine through this exercise. It is the percentile probability of a player winning a game, where 1 corresponds to the first place, obviously, and 0 corresponds to the last place in the match. Now, as we had done once before, here we are going to print the bottom 5 rows of our data. You have again the same 28 columns. And as you can see, as we go to the bottom of our data set, all of our percentile scores are 0 point something. So the next thing I want to be talking about is outliers and fraudsters and their detection and anomalies in a game. Now, for people who are a little experienced with machine learning exercises might know this, but for people who are fairly new to this, I would like to clear one thing out. No data set ever is completely clean and completely correct. We have to do those manipulations and modifications to make sure we can lay analytics on top of a data set. And this data set that we are using is not any different from every other data set. So since it's drawn from multiple game modes, all of the data does not reflect the core gameplay. Now, one more possibility of why some of this data does not reflect the core gameplay is because it might have some fraudsters or imposters. Now, as we all know, we've all grown up playing video games as children or PC games as children. There are cheat codes, there are certain cheats, and you can go ahead and drop this data. But we decided that it's some valuable information while training our model. Hence, we decided to preserve all the data that we have. However, you need to be careful that hackers and custom games exist in your test set, and they are going to in every kind of test set that you draw from any online source. And it is going to distract your model by a certain number. But if you are a data scientist, you're going to have to take a call whether to keep it or drop it. Now, many of these anomalies include killing, say, over 10 people without having to move from a certain location, or maybe you've driven a fairly short distance, like, say, 1.2 kilometers, and you've had already over 5 or 6 road kills, an extremely high number of kills. And I'm not saying like a normal amount of kills, it's like suspiciously a high number of kills, and all of them from really long range. So things like that you have to keep an eye on. Now, apart from that, there is also the case of corrupt data and useless data. Like one I had mentioned before was match ID, which is completely a non-useful feature extraction that we have from the data provided to us, but we are not going to use in this model because, as we had discussed earlier, it contributes nothing to predicting a player's efficiency in a match. Also, a match ID is not a hex identifier string, and it's not ordinal, and due to its extremely high unique value count, you can't even hot encode it as a category. Another is the case of the group ID. Like I said, in every match, even if you're the same 4 people, you have different group IDs. But there is some issues in the API which basically makes it so that if suppose I am in a duo or a squad game, if my system glitches and I have to quit the game and then I decide to rejoin the same game, my entire group ID is going to be reassigned as if it were a new game. With this, we come to the end of our first section. I hope you guys are well acquainted with all these terms now. I'm pretty sure most of you will have known these terms beforehand. It's just for people who are new to this game, and this is only so that people don't have trouble following this model. So again, to summarize, our main goal here is to conduct exploratory data analysis, or EDA. We're going to clean our data. We are going to remove our useless data and detect outliers, fraudsters, find out imposters in our data. Then we are going to feature engineer and generate new attributes and understand how they contribute to the final percentile. And in the end, we are going to use a regression model to generate a list of all the individual player IDs and their probable performance at any given random game at any given random point. So with that, let's move on to our first part, which is to explore our data. So now the first thing we are going to do is to conduct exploratory data analysis. So before going ahead and conducting it, let's see what it is. Now, exploratory data analysis, or commonly known as EDA, refers to analyzing the data given to you so that you can go ahead and find out trends and patterns along with anomalies or outliers in your data. Further, you test hypotheses and make assumptions to come to a statistical conclusion of the insights that you draw from your data. And then obviously you represent it in graphical format for a layman to understand it. So basically you take all of your raw data, you clean it, you sort it out to understand relationships and make that data suitable for analytics to lay on top of. Then you have a distribution plan and arrange your data. And finally, you present it visually so that your stakeholders or your audience can draw meaningful insights from your data. Yes? Now, the main objective here is to maximize the insights that you can draw from your data set and discover the underlying structure that it is present in. Apart from that, you are obviously going to be determining variables, which is most of the times the reason why you create a certain model. You identify outliers and anomalies in that data and take that into consideration for maximum accuracy and test out your hypotheses and underlying assumptions to find out how accurate your model is. So let's go back to our model. So the first thing we're going to do is find out the unique count of personal ID, group ID, and match ID. So let's run this. As I had mentioned before, each player has a unique ID and a group ID, which is used if they are playing in duos or squads. And then again, you have the ID for every match. So as you can see, there are around 1, 2, 3, 4, 5, 6, 4.4 million unique ID counts that we have here. And then you have around 2 million groups that play PUBG. Moving on, as I had mentioned earlier, there are basically 3 modes you can play on, which is solo, duo, squad. There's also custom, which is kind of like a squad, but you guys probably know that. Let's move ahead. Now further, if you go ahead into these match IDs will be of 3 kinds. Match types will be of 3 kinds, predominantly solo, duo, and squad. So if you had to go ahead and segregate your different match types, broadly they would be segregated into solos, duos, and squads. But even inside solos, duos, and squads, you have your different perspectives. You have your solo first person perspective. You also have something known as TPP, which is your third person perspective, so on and so forth. So what we're going to do is we are going to represent these counts based on the different game modes that you can play in. So here we are basically using matplotlib. Here you can find the total number of squads, duos, and solo match IDs. Moving ahead, we are going to go ahead and analyze players in a match and a group. So as I had mentioned before, you can play the game in a solo mode, duo mode, or a squad mode, where solo obviously means you play alone, which is why you have a total of 100 teams of solo people, right? You have 100 individuals playing against each other. Then you have duos, where since the maximum number of players can be 100, you have a maximum cap of 50 duos that can play, and similarly a cap of 25 in case of squads, since squads have 4 teammates. So here what I'm going to do is I'm going to merge 2 lists. I'm going to concatenate 2 lists wherein one list will contain players in a match and the second one will contain players in a group. And for each of them, we'll find out the minimum number of players, the maximum number of players, which is obviously 100 for a match, and the mean or the average number of players for solo, duo, and squad mode matches. Same goes for players in a group. In a match, you have a minimum of 1 solo player, 7 duos, and 5 squads with a mean of 92.9, almost 93 players in a match as duos, around 90 solos, and 94 people when it comes to squads. Obviously, the maximum number of players would be 100 in a match. And similarly, in a group, your mean number of players in a duo is obviously 2, solo is 1, and squad is 3.5. So we're going to round it off early and say 3. Further, we're going to go ahead and print the match IDs of all the solo, duo, and squad games with the maximum number of players, along with group IDs with the largest number of players.
Next, we're going to go ahead and print all the details, players, groups, number of groups, and maximum place of a specific match ID and group ID. And since there are 14 groups, here our very last statement is going to print the probability of each of those 14 groups winning a said match in descending order of performance, starting from 0, ending at 1. So basically, we are ultimately printing out the winning placement percentile for each of the groups in this particular match ID in this particular subset. Finally, what we're going to do is find out the correlation of each feature or each variable that we have discussed before with the winning percentage. And we're going to do it in the form of a correlation matrix, which is represented in a heat map style. So let me just bring it down so you can see both the columns and the rows. And as you might have noticed, as the correlation gets more positive, the color is getting more turquoise or teal, and as the correlation gets more negative or lowers down, the color moves towards a chocolate brown. Yes? So correlation basically is the impact of a certain attribute on the outcome of a variable. Yes? So it's the impact of an attribute variable on an outcome variable. It's like if you're making tea and you have, say, different ingredients contributing to different flavors of the tea, you know one thing for obvious, that sugar has some correlation with sweetness. The more sugar you put, the sweeter your tea will become. Through this heat map, I'm trying to portray something very similar. So if you look here, you can see on the left, I have the winning placement percentile, and in the bottom, there is kills, kill streak, and longest kill. You see, all of these variables, all of these attributes only have a correlation of 0.4, while kill points, match duration, number of groups, and rank points contribute to nothing when it comes to your probability of winning. On the other hand, you have things like boosts, which contributes more than your number of kills. Your boosts is at 0.6, your weapons acquired is at 0.6, and your walk distance surprisingly is at 0.8. So somehow, the more you walk, the more probable you are to winning this game. Interesting, isn't it? Then you can go ahead and find out the correlation of different attributes together. Like, let's find something interesting. Like, if you take up kill place and try to correlate it with revives, you can see there is a negative correlation here. The heat map here shows a light brown color. It's at negative 0.3. Similarly,
you have the DBNOs, or down but not out, negatively correlating to the number of groups as well as the maximum place. But one thing is for sure here, your kill points naturally have 100% correlation with your win points. The damage dealt definitely has a correlation with the number of kills. You can go ahead, keep looking at this heat map or correlation matrix for a number of evidences to find out what attributes impact your probability of winning and what attributes are obsolete, and your chances of winning are completely unaffected by them. With that, we come to the end of our first section. Let's go ahead to part 2 of this model. So the next thing we're going to do is a little feature engineering. Now, what is feature engineering? Basically, when you take attributes of your data that you already have and then process them and take them through some mathematical functions maybe, and create new features or new attributes which can be used to further train your prediction model, it's called feature engineering. How it goes is that you're going to consider all the features that you already have, all the attributes that you already have, and extract some of those. Think of it as a giant pile of data which you're running through a machine, a linear algebraic machine, and then you get your answers on the other side. Now, out of those answers that you get, again, you are going to evaluate the results that you get and then pick out the attributes or the features that you like and think are going to be useful to your model. And if you find out at some point of your model that a certain attribute is not working out quite right for you, you can feed it back into this cycle again till you get the feature that you want. Which brings me to the feature engineering cycle. As you can see, you start out by scoping all of the data that you have, you review it, then you feed it into the feature engineering cycle. Then the feature gets reviewed and gets tried out in your model. Your model is then evaluated and operationalized, and then in the end, you get your user feedback, and then you run it through the cycle again and again till you get an attribute that you need, which helps in training your prediction model further. So let's go ahead and figure out some new attributes which can further train the already awesome data model that we have. So the first thing we're going to do is go ahead and analyze the kills. So the first thing we're going to do is print the average kills by a person. Here we can see the average person kills 0.924 players, which is nearly one player, and 99% of all the people that play have usually less than 7 kills. Now understand this is just an average number. There are people who do attempt more kills than 7. As you can see, the maximum number of kills ever recorded is 72. Moving on, we are going to be using our to plot a kill count bar chart. Here you see your kills versus count graph. Make sure that your quantile or your percentile should be 0.99. And here I've taken the plot to have 15 rows and 8 columns in total. And the entire thing has been sorted in descending order. And as you can see here, it seems like maximum number of people play the entire game without even managing a single kill throughout the game. We can see comparatively how huge this number is. Whereas if we want to look at the number of people who have managed to get more than 8 kills under their belt, now more than 8 could be anything. It could be 9, 10, it could be 20, it could be 30, it could be 50. And as we saw, the maximum number of kills in a game has been more than 70 kills. But yet that number is so little. Now it almost seems like most people can't even manage to make a single kill throughout the game, but at least what they do is inflict some damage. So here again, we are going to be using our training data set to find out the damage dealt by people specifically who have killed nobody throughout the game. Here you can see the damage that is dealt by people specifically who haven't killed anybody at all. Now, there also may be a few people who go through the entire game and even go as far as winning the game without even making a single kill or dealing with damage. So if you try to find out, we realize that more than 16,000 players, which is around 37% of the players, have won without a single kill. And out of them, there are more than 4,700 players who have won without dealing damage. Now, that was all about the individual contribution of killing and damage dealt. But what is the effect of this killing on a certain individual's winning percentage or percentile? Now, obviously, we have observed that the kill count has contributed to a spike or an increase in an average win placement percentage of a player, which obviously makes sense because more kills usually means a player is maybe more skilled and is definitely going to rank closer to the top amongst all other players. So here again, we are going to put a range of kills into separate buckets, which are going to be 0 kills up to 2, 3 to 5, 6 to 10 kills, and 10 plus kills, and put it in a box plot and try and find its correlation with a player's winning percentage. All right. Now this box plot is also known as cats and whiskers plot. And as you can see, with 10 plus kills, you are actually ranking closer to the top. You can see at the end of this chart, there are many outliers though. As you can see, all of these extra dots are actually outliers from the general trend or general pattern of your graph. You can see that not many outliers appear in the 0 kills categories and the 1 to 2 bucket, but as the number of kills start increasing, the number of outliers also increase, which also give us the notion, the idea that yes, the amount of people you kill definitely contributes to your winning placement, but it is not necessary because exceptions are many in this case. Some people may be reckless with this feature. You can go ahead and kill everybody around you, but maybe in close contacts, once you are forced to encounter people as the safe spaces keep getting smaller and smaller, you may not be as good when it comes to closer encounters. Next, after kills, let's go ahead and analyze running. So first of all, we are going to print the number of players who die even before they start walking or they've taken a single step. They've just joined the game. They've just landed onto this unknown island. Maybe they are far away from the keyboard or something else like that. But we realize that a fair number of people, about 2% of the people, have walked 0 meters and have died. Then again, obviously, we're going to find out the walking distance distribution of the players in the top percentile. Then again, we are going to try and find out how running affects your winning percentage. For this, we are going to be taking the help of a scatter plot. Now here we have a scatter plot of the distance someone walks and how it correlates to the winning percentage. This marginal plot or join plot does an exceptional job in helping us understand the relationship between two numeric variables. Now, obviously, we see there is a linear relationship, a direct relationship between the distance somebody walks with their winning percentage. This actually makes a lot of sense to me because winning in a game like this basically means you're the last man standing, which obviously means you've stayed alive the longest. And if you've stayed alive the longest, you've also probably walked the longest. So walking has a high correlation with your win place percentage. With that, we're going to move on to riding. Again, we are going to start out by printing the distance for which an average person drives, which from this we can see is around 600 meters, more or less. Now, there are 99% of people who have driven around 7,000 meters, which is 7 kilometers or less. But there are also people who have taken a ride for over 40 kilometers in the game. As we did before, we're going to find out the ride distance distribution as we had done many times before. I'm not going to repeat it. And we have also discovered that around 3 million players, that is 23% of the entire population, have actually driven for 0 meters, which means that they are more likely to be taking other means such as trekking more than riding. Now, again, how does riding affect your winning or losing percentage? For this, again, we are going to use our scatter plot, a very trusty scatter plot. And again, we see it's a linear relationship, but this seems more scattered along the way as the percentage goes higher. So it seems like there's little to moderate correlation between winning and riding. Now, theoretically, if a player, somebody, can destroy a vehicle, it indicates that they are pretty skilled. Let's go ahead and check if this theory is correct. So here we are going to deploy a point plot to see if destroying vehicles increase your chances of winning. This might take some time. Kindly be patient since this is a more complex sort of cell. And here we have it. As we can see, we have our win percentage plotted against the count of destroyed vehicles. And you realize it does have a really high correlation with the winning percentage. Now, in my opinion, I think it is because of the skill involved. It may not be a direct correlation, but more of an indirect one, because somebody that has the ability to destroy more than one vehicle can be destroyed upon accident, but somebody that can destroy multiple vehicles on purpose obviously is extremely skilled and is going to use that skill to make it to the end. Moving on, let's go ahead and analyze the healing and boosting in a game. Now, healing in PUBG is extremely important, especially after a firefight, and choosing the correct tools to use is even more so. Now, currently you can only heal up to like 75%, I want to say, using your first aid kits and bandages, and the last 25% of your health bar you can restore using any booster item. So by running the first cell, we have determined that on an average, a certain player is going to use 1.4 healing items and 1.1 boost items. 99% of people use either 12 or less healing items and 7 or less boosting items, while the doctor uses 80 and 33 healing and boosting items respectively. So again, we're going to do the same thing that we did a couple of times before. We're going to analyze how healing and boosting affect our winning percentage. Since this is a bigger cell, it's going to take slightly more time. So kindly be patient. Here we're going to be plotting your number of heal or boost items against the winning percentage. And you'll see your heals in a lime green color, whereas you'll see your boost in a blue color. Now, this might solely be this slow due to my internet speed, but I would like to say that it's pretty okay at the moment, and maybe these graphs just take time to load. And I'd also like to remind you again that all of the data sets that I'm using, as well as this model, this entire notebook and all of its code and all of the notes that are given are going to be available in the description box below. So if you need it, go ahead and check it out. You wouldn't be needing to sign in, I'll make sure. And here we have heals versus boosts. Now we can see the heal in green and the boost in blue clearly. You can see both of them are pretty important and pretty correlated with the winning percentage, somewhere up to I would like to say zero point 0.7 percentile. But after a certain while, after 3 heal or boost items, I think boosting becomes more important than healing. And I'd like to guess it's because after 75% of your battery, towards the end, you will be needing boosting for that 100%, which healing cannot raise your health bar up to. Healing cannot provide you that last 25%. For that, you'll have to use your boosts. And if we had to plot each of these separately in scatter plots, you would see the direct correlation between the number of heals to the winning place percentage, as well as the number of boosts with the winning place percentage. Now, both of these plots, as you can see, show kind of abnormal behavior at the 0 point. Now, as a data scientist or a data analyst, you should wonder why that is. It's outliers and anomalies like this which throw off predictions completely. So what do you think the reason is that there are such outliers at point 0 for both heals and boosts? If you have an answer, don't forget to leave it in the chat box and my team shall be happy to get back to you. Now we're going to move on to the effect of killing in different kinds of games. As we discussed before, you have solo, duos, and squads as the different modes in this game. So we've gotten our numbers fairly quickly. We know that we have more than 700,000 or nearly 16% of the games which are solo. We have 74% of duo and nearly 10% that are squad games. Now, if we look at how killing affects each of these different kind of games and their winning percentages, let's go ahead and see what we get. We're going to have our solos in black, our duos in red, and our squad in blue. And these colors are extremely important so that your audience does not get confused while looking at data. Clarity is one of the keys when it comes to graphical representation of your data. So here again, if we bring it down, it looks like the solos and duos kind of have a very similar pattern, a very similar reaction. It's like a logarithmic graph to some extent with certain outliers. They kind of have the similar trend when it comes to the number of kills. However, it looks very different when we take squads into consideration. Sure, the squads also start with a certain logarithmic sort of curve, but after that, it's completely distorted with a lot of outliers everywhere. So the number of kills do not seem to have a lot of impact when it comes to squad games. Now let's analyze the same behavior when it comes to DBNO. It essentially means that your player is simply knocked. They're down but not out, which means they are not killed and hence can continue playing. What they need is revival, and this is a feature which occurs only in duos and squads, because in solos it is every man for themselves, and if they are knocked, it's just an advantage to every other player that is not them. So in a duo or a squad game, a knocked player can be revived or left to die. If suppose a knocked person is revived, you need to understand that the next time you as a teammate will have lesser time to revive them. Now the same can be said about an attribute called assist, which only happens in duos and trios, which basically means you involve yourself in assisting your teammate in a kill. Now, this I would like to leave it to you guys as an assignment. You can solve this and you can leave it down in the comment section below. Once you download this model from the description bar, we will be looking out for some of the best approaches that you can give us. Hope this is a fun little assignment for you and helps you in creating a small little part in this model. There's also a little hint that I've put in here, which is you have to represent it using a joint plot or a scatter plot. It's pretty similar to the section before, so I'm hoping you would not have any trouble here. So go ahead, try it and tell us what you come up with.
So with that, we come to the end of our first part. Stay tuned for the second part, which will go live in a couple of hours, where we'll resume with our machine learning model on this wonderful PUBG dataset.